This is David Spears, civil engineering instructor at Texas Tech University, talking about CE 2301 statics. We've got a 3D rigid body equilibrium problem today. Got this from the book. And it's interesting, and it uses these, what the book calls properly aligned hinges that develop no moment. That's in the description of the problem. At A and B, we have these hinges, and we've got a horizontal plate, might be called ABCE, and we say that these properly aligned hinges at A and B develop no moment, and furthermore the support at B is thrust bearing. So a normal hinge has 5 supports, 5 forces, 3 forces and 2 moments. These have no moment, so they're defined by that, no moment. And so it says the support at B is thrust bearing. That means it has an X force. The thrust is along the axis of the pin, which is the X axis in this case. By implication, that means the hinge at A has no X force. And so we reflect that on the free body diagram in a second here. The goal is to find the reactions at A and B and the force in the cable. Okay, this is a 3D rigid body equilibrium problem. So as such, I have 6 equations of equilibrium to work with. Therefore, I can solve for 6 unknowns, and that's exactly what I have here. Part of the reason I have this thing called these hinges that are kind of unusual. So what we want to do is, first thing, the steps are in these problems are to get 1, a good free body diagram, and 2, to get everything in Cartesian, including the components, and 3, to do the sum of moments and the sum of the forces calculations that are so important to us and help us then solve the problems. So, step 1 is to get a free body diagram. And I've already started that over here because this is kind of a long problem. So I've got a free body diagram of the plate, and a free body diagram, you replace the supports with forces. So at the hinges, in accordance with the instructions, at B I have no moment, but I have BX, BY, and BZ. At A I have no X force, but I do have a Y and a Z and a Y. At the corner, I have the applied load of 1 kilonewtons. I end up calling that W. And then I have this cable over here that goes from C to D. Therefore, I would call it by its endpoints TDC. So, I just need to get the coordinates of these points. In this case, all the points are dimensioned. Therefore, I need to convert those into Cartesian 3-dimensional coordinates. Starting at D, it's at 0, 0, and 1.5 in the vertical, in the Z direction. Point A is right here, negative 0.4. Here's the x-axis coming out to the left. And then I've got everything else along between A and B lies on the x-axis, so the 0 and 0 for the second 2 coordinates of the 3. B is at negative 1.6 and 0 and 0. Point C, where the cable's attached, is negative 2, 1, and 0. And point E, as I've named it over here, where the load is applied, is 0, 1, and 0. Really important to get those because I'm going to have to be doing position vectors and unit vectors and things like that. So that gets everything in Cartesian, and kinda, and we've got the coordinates of all the points. Now I look back at my free body diagram, referring to it. I need to look at the forces and express them in this Cartesian format that I've got right here. Where A, the force at that hinge A, it's really one force, but we think of it as having those two components, AY and AZ. So I write it out in Cartesian form, just like this: 0I, AY in the J, and AZ in the K. For B, it's the same way, except I also have a BX, so I have a BX in this column, BY and BZ. The force W, exerted over here at the right-hand corner at point E, is 0 in the I, 0 in the J, and -1 kilonewtons. In the K, it's negative because it's going down. Finally, the last force I have is the force in the cable. And so I'm going to have to deal with trying to get, or not trying, getting that in its components. So I need a unit vector in that direction from C to D. So what I really need is a position vector first from C to D, like this. We would call it RD over C in our normal nomenclature. And so let's do the calculations up here, and then I'll transfer them down there. So TDC is based on RDC. Well, RDC is tip minus tail. The tip is at D, tail is at C. So I've got the coordinates of the tip, 0, minus 2 for the I. And then I've got 0 of D minus 1 in the J. And then I've got 1.5 minus 0 in the K direction. I do the math, I've got 2I, that's a plus -1J, so that makes -1J. And I've got plus 1.5 K. Something's wrong with my pen. Okay, so that's a position vector, RD over C. I need a unit vector, and so I divide by the square root of the sum of the squares, which is 2 squared, 1 squared, 1.5 squared. And that all works out to be the square root of 7.25. So now I just do the math to get that in decimal form, and all these numbers are times TDC, the force in the cable. So now I'm going to go down here to the Cartesian line I have for TDC, this one right here, and I do the math. And so the first number back up here is 2 over the square root of 7.25. And that works out to be a decimal of 0.743. I use 4 significant digits. I'm only going to write 3. 743 TDC in the I. Continue that. I've got -1 over square root of 7.25 and positive 1.5. So those decimals work out to be negative 0.371 TDC in the J, and plus 1.5 over the square root of 7.25, or 0.557 TDC in the K. That picks up all the forces I have on the free body diagram. There's 4 of them. And so I've already got started here, the work that I'm going to need for sum of forces. That column is the sum of the forces in the x direction. The second column is the sum of the forces in the y direction. The last column is the sum of the forces in the z direction. Each one of those columns has to sum to 0 by equilibrium. Sometimes you can get some help here, but in each column I've got more than one unknown, so I can't really solve this easily. So I'm going to move on. I'm really on step 3, sum of moments and sum of forces now. Like I say, sometimes you can get some help there and get an easy solution. I'm going to have to move on to the sum of moments. Okay, I've got 3 sum of moments, x, y, and z. The point of doing sum of moments is to eliminate unknowns. So I logically want to sum moments about point B, which eliminates all those 3 forces or the components of them at B. And I need to deal with the force at A, the -1 kilonewton down at point E, W, and then the cable TDC. So I've got 3 moments about point B, and the sum of those has got to be equal to 0. Each of these is going to have 3 components. Each of these is a vector, and each of these is a cross product. So I'm taking the moments, let me do it in green, draw my position vectors. I'm taking the moments of the force at A about point B, so I need a position vector from B to A, which we would call R A over B. I need a position vector from B to point E, which we would call R E over B. And I need one to the cable at C, so I need that position vector, which we would call RC over B. So each one of these moments down here is a cross product. So for the force at A, I have the position vector, I have an R cross F. But really the force is A. The position vector is from B to A, so we call that RA over B. Then I have a cross product of R with the weight, the force W. The position vector is from B to E, so we call it RE over B. Finally, I have a moment caused by the force in the cable. That's R cross F also. In this case, the force is the tension in the cable, and the vector is from B to C, so we call it RC over B. So now I see I have 3 cross products. I'm going to have 3 determinants. So let me write them out in a vertical form. I've got MA, which is equal to R cross F, this first one. It's really R cross A. And that's going to give me a 3x3 determinant that looks like this. And then I'm going to evaluate it. I know it's got IJK on the top. I'm going to also do that same thing. And there's going to be some similarities, so I sort of want to take those into account. I've got the moment caused by the weight, or the force. I've called it MW. That's R cross W. And that's a 3x3 determinant. IJK. And then I've got the moment caused by the force in the cable, TDC. I'm really just taking this equation right here and rewriting it vertically. That's R cross F. It's really R cross TDC. And that's another 3x3 determinant. IJK on the top. Now, from up here in my forces, I've got everything in Cartesian form, so I can plug those in on the bottom line. Remember, these determinants are unit on the top, position in the middle, force on the bottom. So I can do all the fill in the force for A. A is the force that goes on the bottom. I've got 0, AY, and AZ from this line up here. Then I've got the weight, which is this line right here from my Cartesian forces. I've got 0 on the bottom, 0, and -1. And then for TDC, I just transfer these values, these decimals, down here to the bottom line of this one. And I've got 0.743, -0.371, and positive 0.557. Everything in that one is times TDC. Now I need to fill in the middle rows for all these, which is the position vector. So let's look at the position vector for the force at A, which is RA over B. Here's my coordinates. So it's -0.4, -0.4, minus the x-coordinate of B, which is -1.6. -0.4 plus 1.6 is equal to 1.2. The others are 0, 0 minus 0, and 0 minus 0. So that line looks like 1.2, 0, and 0. Now I need a position vector from B to this weight, RE over B. It's 0 minus 1.6, so I have positive 1.6, and then 1 minus 0 and 0 minus 0. So this middle row of this second determinant looks like 1.6, 1, and 0. Finally, I have this position vector from B to C, RC over B. I've got -2 minus 1.6. So that one's equal to -0.4. And in the then I've got for 1 minus 0 for this component, for the y component, and 0 minus 0. So I've got middle row of this one is -0.4, 1, and 0. So that's what my determinants look like. Now I just need to evaluate them. And I'm going to go through this quickly, assuming that you can evaluate determinants. And I end up with, like for I, 0 and 0. So I have 0I. What I have here is -j times 1.2 times AZ. So I've got -1.2 AZ in the j direction. And the k is positive k times 1.2 times AY. So I have 1.2 AY in the k. So continue on, evaluate those determinants for yourself. This one works out to be -1I plus 1.6J plus 0K. Evaluating this bottom determinant, I get 0.557 TDC in the I plus 0.223 TDC in the J and minus 0.594 TDC in the K. Now I'm ready to solve it because I see here, by doing it in columns like this, these are the sum of the moments about the x-axis. So that column is sum of the moments about the x-axis. This column is the sum of the moments about the y-axis. This column is the sum of the moments about the z-axis. Each one of those columns totals up to 0 by equilibrium. So I see a column here in the x column that I like because it's only got one unknown, TDC. I can solve for that one. So I write out this equation. I write it out horizontally, and it doesn't have much to it. And it looks like the sum of the moments in the x direction is equal to 0, is equal to negative 1i. Everything's got an I in it. Plus 0.557 in this column, at least. Everything has an I. TDC. I can rearrange that, and I get TDC. Take the 1 over to the negative 1 to the other side of the equal sign, it becomes positive. Divide both sides by 0.557, and I get 1795 or 1.795 kilonewtons for that force in the cable. Once I know that, I can plug that value into these other two columns. This is equal to 1.795, and TDC, same thing over here. So I can then solve those two columns. I could go sum of the moments in the y direction is equal to 0, is equal to negative 1.2 AZ plus 1.6 plus 1.795 times 0.223. I can do all the math, and AZ ends up being, I can rearrange and do the math, it ends up being 1.666, repeating, kilonewtons. The positive means it's in the positive direction like I assumed it. Then I can do sum of moments in the z direction. Rewrite this column here, the z column. It's equal to 0. It's 1.2 AY in the k plus 0 minus 0.594 times 1.795. Do all the math. AY is equal to 889, or 888.8 kilonewtons. Okay, once I know those three values, I can now go back up to my sum of forces columns, and where I've written everything in Cartesian form, go back up here, and I know that AY is equal to 889. So I can plug that in here as 889. AZ is 1667. And TDC, I know that value. Let me do it in blue. So I got 1.795 in every one of those positions. Then I can work on these equations. This first column, sum of forces in the x direction, can be solved to give me Bx, because it's equal to Bx plus 0.743 times 1.795. Therefore, Bx, rearranging, works out to be negative 1333, 1.333 kilonewtons. That's a good answer. And a negative sign is a good answer in Cartesian, in 3D, because it just means in the negative x direction. Sum of the forces in the y is equal to 0. Rewrite this column here. and I have 889 plus by minus 0.371, 1.795. by works out to be equal to negative 222, excuse me, 2.22, I'm sorry, it's 222 newtons, kind of mixing my units, or 0.222 kilonewtons. Rewrite this third column horizontally. Sum of the forces in the z direction is 0. I've got 16. All of these this is 0.889. I'm mixing my units. What did I report down here? This is 0.889 kilonewtons. Getting confused on kilonewtons and newtons. So I got 1.667 plus BZ minus 1.0 plus 0.557 times 1.795. Just rewriting this column here, this Z column. Works out that BZ is positive 1.66, I'm sorry, negative 1.667 kilonewtons. And there I've solved for all 6 of my forces. The 5 reactions at A and B plus the force in the cable. Okay, real quickly, there exists an easier solution at least to get the force in the cable. What I want to do, and it's a very powerful tool, is I can sum moments about a line. So what I want to do is solve for the sum of the moments about line A, the x-axis really, the line running through A and B. So, going down here, what that looks like is the sum of the moment about line AB is the moment of the force W about that line plus the moment of the TDC. Well, this is going on the basic equation of the moment about a line is U of the line dotted with R cross F. So this works out to be really convenient for me. So the moment about W, this position, this determinant looks like, instead of having I, J, K on the top, I've got U, X, the components of the unit vector in that direction. So looking back at the picture, I've got a unit vector along the x-axis. So that is 1 from B to A. Positive 1, it's got no component in the Y or the Z. So that top line of both of these determinants looks like 1, 0, 0. We're taking moments about the line, so it's the same top row for both. The bottom row, I just get my force in Cartesians, which for the weight, it's 0, 0, and negative 1. And for the force in the cable, it's these numbers up here, 0.743, negative 0.371, and 0.557. These are the components of TDC, which I got up here. And I also showed down here in this determinant. And this is all times TDC. Then what I need is a position vector from the line, any point on the line, to any point on the force. Well, that's really a nice position vector. That is, very conveniently, from the line to E is a nice position vector, which we would call RE over, I don't have anything to call it by. But it is just in the pure Y direction. And so it's going positive 1 in the Y direction, does nothing in the X direction or the Z direction. Similarly, down here at the cable, I've got a position vector from the line x-axis to point C, call it RC over something. Observe that it's just also 1 in the y direction. So this middle row, the position vector just looks like 0, 1, and 0. Same one for the force in the cable, 0, 1, and 0. Remember that from the equation sheet, the top row is unit and the components of it. The middle row is position. The bottom row is the force. I have a whole lot of zeros in these things, these determinants, so that really helps me. This works out to be, the only one I have in this first determinant is 1 times 1 times negative 1. Everything else goes to 0. Remember, this is just a scalar. It has no I, J's, and K's. So that works out to be negative 1. Plus, this has also got a whole lot of zeros in it. And the only one that I have is this 1 times 1 times 0.557 TDC. So that's 1 plus 0.557. This sounds familiar to me. It's the same equation that I used up here to solve for TDC. So I can just rearrange it in the same way, and I find that TDC, once again, is 1.795 kilonewtons. Now I would still have to do this moment calculation to get AZ and AY, but this is a quick way to get the force in that cable.